Ladies and gentlemen, welcome. Because this was a jubilee meeting celebrating a 25th anniversary, I took the liberty for my second talk to look back in what I know best, that is my own life, and to look at what has thrilled me mathematically. And as a matter of fact, I would even take the liberty of going a little bit more back than just 25 years. It will be somewhat of a potpourri, the extent to which you can discover a common thread in it, but that's left to you. My first memory of mathematical excitement must have been in somewhere in 1938 or so, as it was at the age that my mother was giving me a hot bath. And I remember that I was very puzzled and annoyed by the fact that I could not determine the ratio of the sides of a rectangular piece of paper so that when you folded it just once that you would get a thing of the same shape. And I couldn't do this. I knew that that ratio had to be somewhere between 1 and 2, obviously, and it had to be symmetrical, but the only hint that I got from that symmetry was a ratio 1.5, and each time that I got 1.5 I multiplied it by itself, and then I got more than 2. And I knew I had to have 2 because I was just folding the paper. And I was very annoyed until my mother explained to me that this check that told me that 1.5 was wrong was a way of finding the answer, and that essentially you had to solve the equation x squared is 2. Well, she didn't use those terms, of course, since we were in the bathroom, but we didn't have pencil and paper, not even a piece of paper to fold. I don't know, maybe she has used a towel, I don't know. But I still remember my excitement that by posing the condition that a number multiplied by itself would have a given product was a way of defining a number. First excitement. Second excitement, I think, was about 10 years later, 5 years later, and that was when I was confronted with the well-known argument that the 8 by 8 square truncated at the end of the diagonal, so it has still 62 little squares, that this cannot be covered by 31 2x1 dominoes. Particularly if you try to demonstrate the impossibility by trying all possible ways and observing that none of them works, then you quickly come very much impressed by the power of the counting argument. And the counting argument is that indeed you should color this as a chessboard. Realize that, first of all, no matter how you place your dominoes, they cover an equal number of white and black fields. However, the two fields removed have the same color, so in the figure that has to be covered, there the two colors don't balance and you can't cover them. I was very much impressed by that counting argument. And that was about 43 or so. I'm making 5-year jumps because now I am in 1948. 8 times b minus c plus b times c minus a plus c times A minus B. Under all standard properties of multiplication, addition and subtraction. What is the answer? Yes, thank you. A number of years earlier, I had been shown the proof that the altitudes of a triangle are collinear. And the argument is this. It's an ugly, very ugly argument, you see. Here we have A, B, and C, and we have an altitude. And now we make another altitude. Yeah. And now, call this, bless you. Now, AC over BC is AC over BC, but both multiplied by the cosine of gamma, which we have here. And AC multiplied by the cosine gamma is DC, and the other one is EC. In short, triangle ACB is similar with DCA, and hence we have here a corner beta and there a comma an angle alpha. Similarity of triangles. Here you do it with the last one, and for the same reason you will derive that this angle is beta. Hence, the altitudes of the big triangle are the angle bisectors of the small one. The altitudes of ABC are the angle bisectors of FED. The angle bisectors go through a single point. That's trivial if you define them as the locus of points with equal distance from the sides of the angle, and hence the altitudes of a triangle go through one point. Now this is a very ugly proof. It's very indirect, and moreover, if you really wish to prove it, of course, you should also analyze that all this is okay for a triangle with an obtuse angle. And I would like you to appreciate that for a non-degenerate triangle, this is a proof of the fact that the altitudes go through one point. You see, here we have an origin, and this is a vector A, and this is vector B, and this is vector C, and therefore this is A minus B, and this one is B minus C, and this one is C minus A, or what is it? Yeah. Or plus or minus, doesn't matter. The fact that the sum of these three quantities is 0 tells us that if two of these values are 0, so is the third. Now interpret these A, B, and C as vectors, the addition and subtraction is normal vector addition and subtraction, and for the multiplication we take the scalar product, which has all the distribution and symmetry properties, and therefore if two of these terms are 0, the third is 0. That is, if two of these vectors are orthogonal to their opposite side, so is the third. I was very thrilled when I saw this simple calculational argument that the altitudes of a triangle go through a single point. I can leave that. Now the steps become a little bit smaller because my next thrill I had in 1951, and I'm glad to report it here, not only because I got the thrill in Cambridge, but even more so because the author of the thrill is in my audience. One of the annoyances of my high school years was that I had several tables of logarithms. I had even an old, very thick, high precision one, which had been inherited from my mother, and I had played lots with it, and I knew how you could use a logarithm table at good advantage. But no one could give me very clear indications of how several centuries earlier those logarithmic tables had been computed. The rumor was that people knew that the logarithm of 1 was 0 and the logarithm of 10 was 1, and hence the logarithm of the square root of 10 was 0.5, and so on. Yeah? Anti-logarithms was a term that we... And the suggestion was that by repeated computations of square roots, numbers with known logarithms had been computed, and that as a result from with interpolation the logarithmic tables had been formed. To the best of my knowledge now, that rumor is correct. I knew how to compute square roots with pencil and paper, and it was a process that I didn't like at all. I realized that if you were going to do this your life, that you would get a certain proficiency in it, but it sounded most unattractive. And then in Cambridge, where I was introduced to programming, there was a lovely little booklet, and that lovely little booklet also contained a number of subroutines, and as a matter of fact it contained 2 subroutines to compute the logarithm. Lo and behold, here was an algorithm using multiplications and very modest things only, that just could compute an isolated logarithm. And I looked, and I was very excited. And I will show it to you in decimal, although the EDSAC being the EDSAC that it was, it did of course in binary, which has further advantages. What do we know of the logarithm, the decimal logarithm of a number? Well, the integer part. You see, because from here till there the logarithm starts with 0, something, and from 10 to 100 they start with 1, something, and from 100 and to 1000 it is 2, something, yeah, and then it's 3, something. That is, for a number less than 10 to the 10th, we see the leading digit of the logarithm at a glance. Now suppose that we wish to compute an arbitrary logarithm, logarithm of 2. Wish to compute logarithm of 2. Yeah? Well, the logarithm of 2. Well, start with 0. Yeah, A, B, C, etc. Now everybody who has ever programmed for a binary machine on a level at which you needed to know that it was a binary machine and wanted to write a routine that, given the binary representation of a fraction, would give you the decimal representation of that function, he knows how to compute the digits A, B, C in succession. You see, A is quite simply the entier, the first digit. Yeah? If this number is x, then the first digit behind the comma is the entier of 10 times x. So in order to, we define that A that we are looking for as the entier of 10 times the logarithm of 2. But that is clearly the entier of the logarithm of 2 to the 10th. But that we can compute. It is the entier of the logarithm of 1024. And since 1024 is in that range, has 4 digits before the comma, the logarithm of 2 starts with 3. Okay. So, and then you remove that and ask your question, what is the B? Well, in the meantime, the removal of that 3, now you have to raise 1,024 to the nth power, and then you'll discover that you are still under 10, so it is 0. Yeah? And that number again you raise to the 10th power, and then you discover that you are just above 10. Yeah? And the decimals of the logarithm 2, 3, 0,30102, they come out of it one after the other. Lovely, lovely, lovely. Now David Wheeler is the author of this routine. Only wherever I said 10, you should replace it by 2. Great excitement. 1951. The next excitement is a story that has been attributed, rightly or wrongly, to the late Stanley Gill. Good old Euclid's algorithm. Yeah? Here we have x at least greater than 0 and capital Y greater than 0. And our algorithm is the following: x comma y becomes capital X comma capital Y, and in doing so we establish that the greatest common divisor of x comma y equals the greatest common divisor of the lowercase x comma y, and x positive and y positive. A relation that will be maintained by the following program. Well, I'll leave some room. If x exceeds y, then x will be decreased by y. Alternatively, if y exceeds x, then y is decreased by x. These tests guarantee that little x and little y remain positive. The sum decreases Therefore the program terminates. When it terminates, both guards are false. So x is at most y and y is at most x. That is, x and y are equal. And if x and y are equal, then we know that their greatest common divisor is, what is it? X or y. We'll print it, Print, well, since I can't make up my mind whether to print x or to print y, I will print their average. No. After the age of 8, of course, I could have printed the square root of the product, but this is, as you see, a purely additive program, so I had better print the average. Huh?
Could surprise you with overflow in even more cases.
Oh, yeah. Yeah, okay. Now I'm going to embellish this program according to Stanley Gill. You see, I introduced two new variables, u and v, and they have to be initialized. And in order not to destroy the symmetry, I will initialize them with capital X and capital Y. Having done so, we shall do something with u and v, and in order to make it nice, we say u becomes u plus v. And of course, in order not to destroy the symmetry, we will v becomes v plus u. So that is nice. But now of course we have to print something. What shall we print? There's no point in computing u and v if we don't print something. What do we print? Average, of course. You are dull that you don't guess this. Print. Now, you may wonder, of course, whether u plus v is even. It so happens that u plus v is even, so this does not give all sorts of difficulties with truncation or round off or what have you. Question is, what number is printed here? Yeah? Now, this is the greatest common divisor of capital X and Y, and this prints the smallest common multiple of X and Y. Ain't that charming? Now the argument that it does so. See? Little u and little v satisfy the following invariant. 2 times x times y equals x times v plus y times u. That's clearly true upon initialization when this term becomes xy and this term becomes xy. Furthermore, it remains invariant during such an assignment, you see, because in this assignment, when x is decreased by y, this term changes by minus y times v. But when u is increased by v, this term changes by plus y times v. And therefore, the right-hand side does not change its value. And of course, for the other alternative, similarly, now, upon completion, both x and both y are equal to the greatest common divisor. Divide both sides by it, and you find that 2xy over the greatest common divisor of x and y is u plus v. Yeah, but this is divided by 2. Yeah? But the product divided by the greatest common divisor is the smallest common multiple of x and y. So there we are. Now, it was this totally simple argument that gave me a great thrill. See, because if anybody doubts about the power of the notion of an invariant in proving things about programs, you should show this example to him. This is absolutely the simplest way of... As a matter of fact, I would know of no other way to demonstrate that upon completion u plus v over 2 is the smallest common multiple. I can't precisely date that.
Then you don't have to divide by 2, is that correct?
I never do that because if one of the numbers is 0, then...
No, I mean, instead of saying ub equals xy, set ub equals x, 0. Then the invariant becomes xy equals...
Yes. Yes. But that would destroy the beautiful symmetry.
Okay.
We would never do that. We would never do that.
Not till the last minute.
Well, I wished that I had a symmetric way of writing u plus v. Yeah? That I had a symmetric way of writing down an unordered pair. Okay. Now I'm not going to make a great jump. Types of arguments that excite me, that thrill me. I'm considering n couples, man and wife, husband and wife, contrary to Don, who was this morning forming those couples. I'm now considering existing couples, a finite non-empty number. So there are n couples. I allow myself a single some linguistic liberty. This morning we heard about stable husbands, although it was really something else that was stable. In this building there are such things as disabled toilets. I'm going to talk about male age and female age. Yeah? Okay. The given thing is the maximum male age equals the maximum female age. Yeah? That's given. And furthermore is given that if two couples after a wife swap between two couples that is asymmetric, yes. In the United States you get in trouble if you do this, but I have decided to be a politically most incorrect teacher. So after a wife swap between two couples, the two new combinations yield the same, or have the same minimum age. Yield, have, I'm not quite sure about which verb to use. It's clear? It's given. If two couples perform a wife swap, then the minimum age in the one new combination equals the minimum age in the other new combination. Is that a better formulation? Yeah? Okay, then I will rephrase that. Yeah? The minimum age of the one new combination equals the minimum age of the other. New combination. Yeah? And the demonstrandum is that in each couple, male age equals female age. Yeah? You have to show that in each couple, man and husband and wife have the same ages. I'll give you two proofs for this. And then you can compare them. The one proof is a two-stage proof, because we first establish a lemma, and that is there exists a couple with both ages maximal. Yep. Now the argument is as follows. There exists a man of maximum age. Now here we put that man, yeah? And the fact that he is of maximum age I will indicate by writing a little big M with it, yeah? So here's a man of maximum age, but there's also a woman of maximum age. Now, either they are married, and then we have established our demonstrandum. If they are not married, then this man is married to some female, and this woman is married to some male. So here we have two couples. However, if the top couple and the bottom couple perform a wife swap, then the new combinations are the left combination and the right combination. I hope that people that know that I do not like pictures appreciate how sweetly here I use the two-dimensional blackboard. And now we apply that afterwards the two combinations have the same minimum age. Now the minimum age here is obviously capital M, the maximum age that occurs in the whole lot. And therefore it is one here as well, so we can plug an M here and an M there. And we have established that prior to the wife swap there exists a marriage with at least there exists at least one marriage where both women are of the same age. Okay, so now we have established our lemma. Yeah. Now we have that. Now we have found a couple of maximum age. We're going to use them, and we consider an arbitrary couple. Now we have two couples, the couple of the maximum age and an arbitrary one. Okay, we perform the wife swap, and we have a left combination and a right combination. Well, if this has the age f, little f, and this has the age little m, then the minimum age here is little f, and the minimum age in the other combination is little m. But we are told that they are equal. So we see that of the new couple, the ages are equal. End of proof. Everybody buys this argument? I'm not sure, but... Huh? Yeah? Some of you at least buy it. Yeah? I hope. Now a completely different style of argument. Let's calculate. Let's calculate. That is, let's manipulate formulae. Now then, first of all, I wish to demonstrate, to formalize what has been given. Now, let little x and little y range over couples. Let mx be the male age of couple x, and let fx be the female age of couple x. And so for y. Now the first thing that has been given, 0, is that the maximum male age equals the maximum female age. Well, how do we write down that? The maximum over little x, over couples, and the value I take the maximum of is the m of x. I use this as the maximum over x, over the couples, of the male age of these couples. And the upward arrow and the funny brackets are a quantified maximum taker. It has been given that that equals the maximum over x of the female x. So that's the first thing that has been given. The next thing that has been given is the wife swap. Well, have a look. If we have couples x and y, then the two ages occurring in the one new combination of the y is the the male age from the y couple and the female age of the x couple, and in the other new combination we have the male age, we have the female age of the y couple and the male age of the x couple. And that being so, we say, well, the minimum of this, and I will write this with an infix downward arrow, equals the other minimum. So with the convention of a downward arrow for the infix minimum, I have now described that the wife swap leads to new combinations with equal minima. Now be careful, the original statement, verbal statement as there is, tells you this for x and y different. So it has been given that this holds for all x and y such that x differs from y. However, if x equals y, then it also holds for reasons of symmetry of the minimum operator. So this is unrestricted for all x, y. And now the only thing I have to do is to compute that mx equals fx for arbitrary x is true. Am I going to do that? No, I'm not going to do that. I'm going to compute that m of y equals the f of y for arbitrary y. Now, how do we do that? Well, my proposal is to rewrite this expression without changing its value. So I'm going to transform this expression to value preserving rewritings. Now, to start with, we will just rewrite the left-hand side without changing its value, and we will rewrite the right-hand side without changing its value. Now, what is the purpose of that rewriting? The purpose of the rewriting is to get these things in such a shape that I can use 0 and 1. But 0 contains a quantified maximum. So I can only do it if I seek a possibility of introducing a quantified maximum. 1 contains an infixed minimum. So I can only appeal to 1 as a rewrite rule if I succeed in introducing somewhere an infixed minimum. Now, what do I know about the m dot I, the male age in capital Y, and the maximum of the male ages? M dot Y and the maximum of the male ages. Well, since this is from one of the couples and the maximum is taken over all the couples, this maximum is at least m dot y. But in general, if A, the statement A is at most B, is equivalent to the fact that the minimum of A and B equals, the smallest one, A. So, we come to the conclusion that on account of the up-down calculus, and in fact we use the law of absorption, the m dot y is the minimum of itself and the maximum male age. So there we are. The maximum of x, m dot x. Funny close. And at the right hand side I do exactly the same thing. I say, well, the f dot y is equal to the f dot y minimum, and now the maximum over x of the female ages. And you see that at a single stroke I have succeeded in introducing both my quantified maxima and the infixed minimum.
X belongs to y.
Yes. Thank you very much. Okay. But now I can appeal to 0 because now the expressions that are given to be equal, I can therefore replace the one by the other. left-hand side does not change its value if I take the m dot y and now the minimum over x of the f dot x equals, and in order not to destroy the symmetry, I replace that one by not the maximum female age, but the maximum male age. So I've used 0. Now I have to use 1. Oh. Well, 1, I can only use that when I have that infix. You see, sorry, I made one, I skipped one motivation. The fact that I appealed to 0 by interchanging these terms was partly inspired by the desire to use 0. It was also inspired by the desire to use 1. And I can only use 1 provided I have males and females at both sides of my infix minimum. And now I have males and females and males at both sides of the infix minimum, so I'm in good shape. However, I cannot use 1 yet, because that talks about a minimum between 2 occurring ages, an x and a y. Now, fortunately, and that is a rule of the up and down calculus, and that is that down distributes over up in exactly the same way as and distributes over or and its existential quantification and all those things. That is, and if you didn't know this, you would discover that this is a necessary lemma to prove the whole theorem. I suppose that people know the up-down calculus, and then this is rewritten as the maximum over x of m of y down f dot x. And the right-hand side, similarly, is written as funny open, the maximum over x colon colon, the f dot y down the m dot x. And now we are in a shape to appeal to 1, because 1 states that for all x and y, these two expressions are equal. Hence, when you quantify over them on account of 1, this is true. So there we are. Four steps, 2 appeals to the up-down calculus, and 1 appeal to each given once. I love this argument, and the reason why I love it is because I can present it without pictures, because this is the type of argument one can construct without any invention, just by looking at, I'm tempted to say the symbol dynamics. It's quite clear that if you wish to use 0 and 1, you have to use them, that you have to introduce the single minimum and the quantified maximum. Yeah? And the only knowledge it uses is some knowledge over the up-down calculus. But that is a very general topic, and it is not unrealistic to assume that that belongs to our luggage. Yeah. Well, that is about it. There are there's one thing that I would like to point out, and that is that if you wish to show that some predicate that depends on the expression x, which I assume also to be a predicate, but that's not essential, and this is everywhere true, then in the case that f is monotonic, which is a regular situation, one of the most fruitful ways of rewriting this is that there exists a z such that z is stronger than the expression, and everywhere the f of z holds. Now this is an extremely pleasant possibility of rewriting. The reason that it is so nice is that the expression may be of a form such that the place in which it occurs in f makes it difficult to manipulate there. However, here we have x as the right hand, as the consequent, and in that uncomfortable place we now have a variable. And that gives you the room for lots of manipulative possibilities. In particular, it gives you the freedom to choose a nice z. For instance, we choose the strongest z that satisfies this condition. Because the stronger you choose the z, the easier it is to demonstrate this. Now you see, of course, now you see, but that strongest set, in order to apply the trick, that strongest set has to exist. Yes. I have encountered many theorems where, in order to prove this, the existence of a strongest set satisfying everywhere f is an essential part of the theorem. With another f, you cannot prove this. So another way of looking at this is that it is a way of exploiting the fact that this viewed as equation in z has a strongest solution. Similarly, now you can also rewrite it as for all z such that the x implies z, the f of z. This rewriting is indicated if x has such a shape that you can nicely manipulate formulae if you, with exp in the antecedent but not in the consequent. Now, obviously these two rules are extremely general, and I do not have the time to demonstrate them, but believe me, if you apply them, then the existence of a strongest solution for this, that of course smells of the Galois connection, and the whole apparatus tells you what to do. Sorry that I cannot go into details. Questions? Remarks? Objections? Yes.
To the title of your talk, not to any of the content. Things I've learned and liked.
Yes, the kind of.
The kind of things I've learned and
Yeah.
liked. I just wondered whether, having chosen that title, you gave any thought at all to any of the following: interrupts, semaphores, multi-programming, levels of abstraction, etc.
Yes, I did. And I decided not to mention them.
Would you like to explain? Had you been given more time, would you to talk on just that matter?
Oh. I might have told that my reason for introducing semaphores was because I wanted to move the arguing and showing the correctness of operating systems, to be able to do that in discrete reasoning without any analog arguments. I would have told that for years and years I assumed that that was precisely the same reason why Maurice Wilks introduced microprogrammed machines. That did not turn out to be true. Maurice Wilks' choice, he told me, was purely inspired by economic mechanical considerations. I would also tell that for the first 5 or 6 years that I taught this material, I had the gravest difficulties in convincing my audience that it was a worthwhile exercise to try to argue about the cooperation of such processes without taking their relative speed, velocity speed into account. Speed, you see, yes. Each time the public protested, because I knew the speed ratios, didn't I? And not using that, ignoring that, I threw away valuable knowledge. I've had a hard time convincing people that since the only thing you can do with knowledge is use it in the argument, the only thing the knowledge can do is to complicate your argument, because you have to use it. Nowadays, well, we can argue two ways. Either we can say that communicating and cooperating processes with roughly undefined speed ratios is a familiar abstraction, and therefore people don't protest anymore. But I think that the explanation is a little bit more encouraging, and that people don't protest because they are more aware of the fact that we have to abstract. I hope so, at least. So that will one be